Hi, everybody. Thank you for coming. Today, we're going to have a little bit more linguistic kind of talk. Today, Leonie Weissweiler from the Center for Information Language Processing at LMU Munich is going to do a really interesting talk about the linguistic perspective of NLP. She finished her bachelor's and master's at the LMU in computational linguistics and computer science. She received scholarships from the German Academic Scholarship Foundation and the Max Weber program. Her current research interests are emergent structure in language, interactions between cognitive linguistics of NLP, construction grammar, automated cross-lingual linguistic analysis, and I'm just going to post her page so you can check out her papers, her publications. And yes, so we're going to do a little bit more linguistic side of NLP. Feel free to just write any questions in chat, and I'm just going to politely interrupt her and ask the questions from chat. So thank you, Leonie, and yes, thank you. And also, yes, she's a PhD student under the supervision of Professor Schütze, and yes, thank you for coming.
Yeah, thanks for the introduction, Martin. Yes, so like I said, please just interrupt me at any time if you have any questions. So let me just, I hope you can already see the slides. If at any point something goes wrong, please just interrupt me and I'll try to figure out the technical details of this. All right, so I thought we could have a bit more of an introduction to what's interesting about linguistics from an NLP perspective today. Originally, when I was asked to give a talk, I wanted to jump straight into my research, which is very much in this sort of linguistics niche, but then I thought maybe it's nicer to introduce this sort of way of thinking to a broader audience first. So this is a version of a talk that I originally prepared for general AI summer school in last year, slightly adapted for this audience. I hope it's going to be accessible. If at any point I assume something that you're not familiar with, please just interrupt me at any point. So I've entitled the talk, The Past, Present, and Future of NLP from a Linguistics Perspective. And the reason why it's so historical is that I think the most interesting way to talk about linguistics and NLP is to go back and look at how they evolved together. There's so much shared history between how NLP evolved and what happened in linguistics in like the last 100 years even. But I think a lot of people who come into NLP nowadays are not necessarily familiar with. So I always think that's so fascinating to talk about. And then I think it leads very nicely to how we can use linguistics to talk about some challenges that NLP is facing today and how they can be really interesting and informative, even for people who wouldn't describe themselves as intrinsically interested in language and in the science of language. So I've structured this talk into asking questions. That's basically what I'm here to do. That's also why I'd really enjoy to have a discussion in the end. So the questions that I'm asking are, what is the structure of language and how do we acquire it? This is one of the major questions that's been keeping linguists occupied basically forever. So I'll go over a brief overview of how thinking about the answers to this question has evolved. So this is more in the area of language structure, which we also call syntax. I'll get more into that later. And then in parallel, I'd also like to talk about the historical development of how do we think about the meanings of words and meaning in general. After I cover that, we get to the really interesting current part, which is what do transformers have to do with any of this? Do they stand somewhere in this debate? And then the reason why I think this is so interesting to talk about right now is where do we then go? So to start off with, I'd like to talk about what is the structure of language and how do we acquire it? And I think this is best discussed by looking at an example that's been a controversial topic for pretty much the entirety of the modern debate of this, let's say the last 50 years. Which is the English past tense, which maybe if you've never thought about it, seems like a pretty obvious and simple thing, but there's something really interesting here. So there's a debate about how language works in the brain, and we're going to take English past tense as an example of this. So how people would describe the English past tense is that if you think back to English classes, if you're English second language speaker or third language speaker, you get regular forms. You do the past tense of need as needed, and then you'd have to memorize a bunch of irregular forms like is to was, goes to went, comes to came, etc. And linguists have been studying this for child language acquisition, so first English as a first language speakers for some time. And there's something really interesting here, which is that children essentially go through 3 stages in learning how to form the English past tense correctly. And the first one of these, in the first line of the table, so what you can do is you can subdivide all of the verbs of English into some that you learn really early. So the early verbs, what we mean by that is really high frequency ones, like is, was, or goes, went, that children would be using all the time. So that's something that they acquire initially, and they acquire it completely with the irregular forms that go with it, just out of necessity. But then what's interesting is when you go beyond that, we can categorize the verbs into different categories, which would be you get the regular ones, like need to needed, and then you get the other irregular ones. So there are irregular verbs in past tense that are really not that frequent, right? Like teach, taught, for example. And then the last column here in this table is, wait, let me just, guess I can get a laser pointer. Yes. So the last column here is what do children do when you present them with a made-up word, which is really, really interesting. So if you just make up a verb and you just see what sort of past tense they give you for it. So what they found happened when children tried to learn English past tense is that after this stage, where they're just doing the most frequent ones, they get to a second stage where they now acquire the regular form, but they over-regularize everything else. So they even sort of go back on the verbs that they were doing correctly, and they now would over-regularize to goad or to comed, for example, if we take these. And the other irregular forms, they would also over-regularize. And so it's the same for the novel forms, for the made-up ones. And only then, once they get over this over-regularization stage, do they reach a point where they can handle the early, really frequent verbs correctly and the regular ones. And then they still need more time to get to the point where they can learn the irregular forms. That sort of happens more slowly over time as they really learn about these words. So this is like a classic example for the debate, which is how do children learn this? And then eventually we get to the point of how could machines learn this? So to understand what the debate is about, let's first look at one side, at one camp in the debate, which is that of Noam Chomsky, who in 1957 wrote a really influential book called Syntactic Structures, in which he explained that he thinks that humans learn some rules of language. So the quote here is that language is a system of rules that in some explicit and well-defined way assigns structural descriptions to sentences. So how this would work in terms of the structure of a sentence, for example, is you get this really regular tree. Maybe some people have seen stuff like this before. You get binary branching trees, and they sort of, you get rules for producing these trees, and they account for everything that's going on in sentences. So you get rules, they look like this, and then lots of rules, and then these are like syntax level rules. And then eventually you'd also get down to rules about the past tense, which we just talked about. So you'd get a rule like past tense is done by attaching ed to a verb, and then that's a rule. And then separately from the rules, you get a lexicon where you now get to store all of the irregular forms, like is, was, goes, went, and so on. And so the idea here is that there are rule learning principles at all levels of language, and the brain has to acquire these. And now The question, of course, is how does the brain acquire these rules? And Chomsky's answer is that rules are an innate bias. The argument goes like this. They said that the poverty of the stimulus means that the data that children are exposed to, basically everything that we speak to them as they're learning how to speak, would be consistent with an infinite number of possible grammars, because it contains no negative feedback. Now, this is something that's really controversial, because at the time there wasn't really any study when he first said this about how much data are children actually exposed to, and do they not contain negative feedback? And also, what's going to be really interesting is the question of, is it really so bad that it contains no negative feedback? They also said that about the data, that it's degenerate in terms of scope, so just not enough data, but also in terms of quality, and that adults also don't talk to them correctly all of the time. And that also the children are all exposed to different stimuli, and so that there's no way, therefore, that they can just acquire these rules from this really disorderly and poor data. And the solution that Chomsky came up with for that is something called the language acquisition device, which is basically a bias for this sort of tree-based grammar structure of rules that is hardwired into the brain. And this is something that's called universal grammar. So the idea would be that in the brain, you already have, let's say, hard-coded certain biases, and now they're just options for language diversity. For example, some languages might have adjectives before the verb, some might before the noun, some might have them after the noun. And children simply have to choose from these options, and that's how you would get by with this little data. And now it gets really interesting, because 10 years later, there's a study that's arguing for the exact opposite by some cognitive scientists called Rumelhart and McClelland, who now argue that humans can actually learn, but not with rules and a lexicon, but with what is essentially the first version of a neural network. So they again worked exactly on English past tense, and there was a lot of manual stuff involved, but what they said was that implicit knowledge of language may be stored in connections among simple processing units organized into networks. And acquisition now occurs simply by a process of adjusting connections between units. So I hope that you can all see how this is sort of a really early version of a deep feed-forward neural network. Now, there are some problems here, which is that there's a lot of manual feature engineering at the beginning of this network, and also there are some shortcuts that are taken at the end. But they demonstrated in an actual learning process that you could acquire the past tense of English without having to have explicit rules, but you could store the regular forms and the irregular ones in the same network without needing any sort of explicit representation and without needing a separate lexicon. Now, this was really cool, but then 2 years later, there's a very influential rebuttal by Pinker and Prince, who point out a bunch of issues. They point out that the Rumelhart and McClelland model only turned out to be correct in 67% of the cases, which was progress, but still a major problem. That's just not enough. And then they start on a line of questioning that sort of continues much later, which is, as it does make errors, what are the errors like? And they argue that the errors that the neural network made were errors that a human would not make. So not over-regularization, but instead weird mixed errors, like making ated out of eat, which is sort of like a mix of ate and eated. They also do over-irregularization, which is something that humans basically never do, which is when you're presented with ping, not to say ping, but instead to say pang. And this study, I'm not going to go into the details, but basically this study was so influential that there was a widespread skepticism towards neural networks for modeling any sort of linguistic data and for modeling human cognition among linguists and cognitive scientists that basically persists to this day. And that's really interesting because they had early neural networks, they were working on applying them to language, in a sort of unsupervised way. But then this early failure and people pointing it out sort of led to the idea that neural networks are a complete dead end for modeling how human language works in the brain. And that's really interesting, and that's something that's only now slowly being rethought. So let's jump forward in time a bit to when this issue was next picked up, the one of English past tense, which is after neural networks were already popular. So I'm just going to assume you're familiar with modern developments in RNNs, and let's jump ahead to the next study on this, which is in 2018. Well, not the next one, but the next big one, by Christo Kirov and Ryan Cottrell, who took encoder-decoder networks with attention, which were the sort of the most up-to-date thing that they had back then. So, you know, your basic character level RNN with an attention layer. And they now looked at, could this model learn English past tense more satisfactorily than the original attempt by Rummelhart and McClelland? And so what they found was that, so this is a graph from the learning on the training set. You get the training percentage on the x-axis and the accuracy on the y-axis. And now let's first look at the blue ones, the ones to do with single task. So in dark blue, you get regular verbs, which are learned perfectly almost immediately. And then in light blue, in light dotted blue, you get all verbs. But what's really interesting is that in the red line, you get irregulars. So they showed that this RNN can acquire the forms and that it learns the regularization really quickly, and then the irregular forms sort of slowly over time, which starts to somehow match the human data that we had before with the 3 different phases. And what's even more interesting is that they find that this works even better if they don't only train on English past tense verbs, but also on other morphological phenomena, which makes a lot of sense because it's not like children only learn English past tense for the first few years of their lives. They learn a lot of other stuff. And so you see that given the multitasking, the irregular forms are picked up even quicker by the model. And so they compare their final accuracies to the MGL is basically an implementation of the ideas of Pinker and Prince, minimal generalization learner. Just think of it as the most up-to-date representation of a rule-based network working on this. And they found that they achieve higher accuracies for encoder-decoder with encoder-decoder models, both for regular and for irregular verbs. And they basically see this, so this is in 2018 with the Tackle paper, they basically see this as a modern day rebuttal of Pinker and Prince. And now they're again arguing, and this is why this is so important to linguists, they're now again arguing that it is possible to acquire this sort of generalization without an innate system of rules, without a bias in the brain for rules and a lexicon, and that is why it's really important. But then history sort of repeats itself, and a year later you get a paper by Maria Corkery and Sharon Goldwater called Are We There Yet?, who re-examine this result and re-examine the model that Kirov and Cottrell built and find that it actually wasn't sufficient. So they looked at irregular and regular verbs, but what's really important is they looked at studies on real verbs. So, you know, the normal English past tense verbs, and they found that they could replicate the exact accuracy, so that was great. But they did find that over multiple runs of the model, there was a lot of instability, which wouldn't happen to humans. But then what's really important is what happens to nonce words. So those are like made up words. And they found that the model doesn't produce what humans would produce, which would be that humans would produce regular forms for nonce words a lot more often than the model. So the model again was making an error that humans wouldn't, which is to have too many irregular forms. And that's basically where this debate left off. So the discussion sort of remains open. If you can get a neural network with limited data, I mean, I'm not talking about can you get an entire ChatGPT to learn this. I'm talking about can you get a realistic model with a realistic amount of data to learn this specific pattern of regularities and irregularities without giving it a bias for rules. And if that could be shown in NLP, that that's actually possible, that we can simulate the human results on these studies, that would be a really influential statement back to linguistics. But basically, that hasn't happened yet. So this was sort of an overview about the structure of language and how it's evolved in linguistics alongside with NLP. And now I'd like to take a step back in history, but look at it from a different angle, which is to talk about what is the meaning of the word and how is it represented in the brain. So here's an early theory of that, which has a lot to do with what we're doing with language models right now, which is called distributional semantics. So in 1957, there's this quote, "You shall know a word by the company it keeps." That's in 1957. Modes of meaning basically coined something called distributional semantics, which is what we still do today. So the standard example would be, if I give you a sentence like this, "He filled the wampum with the substance, passed it around, and we all drank some," then you get some idea from the context of what sort of properties a wampum might have, even though I have not given you any sort of definition. And if I then give you a different example sentence, like "We found a little hairy wampum sleeping behind a tree," suddenly you have a whole other mental image, right, of what a wampum could be. So it turns out that we have learned something about the wampum purely from context. And now what's really interesting about this is what we're currently using for word embeddings, right? But it doesn't just have to be that. You could also use this as a pretty radical theory of how meaning works in the brain, that basically all of meaning is the context in which it appears. But as we're doing opposing viewpoints today, let's first look and go and look at the opposing viewpoint, which came around in the 1970s, and it's something called truth conditional semantics. So they have completely different ideas of what constitutes meaning. They talk mainly about sentence level, but it basically works out to something very comparable. So the idea here is that the meaning of a sentence is the number of possible worlds in which the sentence is true. So therefore, to understand what a sentence means, you have to evaluate exactly what these sort of conditions are. And so the standard example I always think about is like if you say elephants are pink, then under truth conditional semantics, the meaning of this sentence would be the set of the possible worlds that all have pink elephants in them. So what they now do is they now really concentrate on how you can formalize these truth conditions. So if you look at a sentence like this, if Socrates is a man and all men are mortal, then Socrates is immortal. And what you can do now is you can sort of formalize this into a formal semantic representation that's kind of like this, where you make man a property and you introduce some variables, A and X, and you bring it into a form of propositional logic. But in my personal opinion, and the opinion of a lot of other people, this is kind of really threadbare, because there's a lot of stuff that doesn't work with this. So what about questions, for example? If I ask a question, are elephants pink? Is the meaning of "are elephants pink" now also the set of all possible worlds in which elephants are pink? And then what would make it the meaning of a question? What about commands? What about if I say elephants may be pink? Then what exactly is the set of possible worlds for that? What about if I'm just expressing my opinion? What about if I'm just saying, I believe that elephants are pink, but also if you go away from the possible worlds and if you just think about this sort of representation of a sentence, then how do I even, with this sort of logic, represent a question? This sentence, I mean, if you look at this sentence about Socrates, I think you can sort of tell that this is a sentence that somebody wrote in such a way that it would be easy to make an example of this logical form with, but it's not just a random sentence that somebody actually said that they drew from somewhere. So this is sort of a very compositional and very formalized approach to sentences. And now there are people also in the 1970s who have the exact same attitudes about word meaning, which are called componential analysis. So the idea here is you can analyze the internal semantic structure of a word as composed of a number of distinct and minimal components of meaning. So let's just look at an example before I waste time trying to explain this very complicated sentence. So the classic example, if you want to compare cats, pumas, dogs, and wolves, then you would come up with distinct and minimal components of meaning, which are animate, domesticated, and feline. And then each of those you would represent as a combination of these features. So that gives you a way to distinguish all of them. Like none of them has the exact same combination of features, right? So this is also something that could maybe remind us of feature vectors, of manually designed feature vectors. So that is one way of answering the question of what is the meaning of a word. But then on the other hand, also in the 1970s, you get prototypes introduced by Eleanor Roche. So prototypes are something like this. She made a really interesting experimental where she went and asked participants in a study to tell her how much they considered different birds a bird. So birds have been really controversial as like an example of word meaning, because it's really difficult to come up with a definitive set of features that define a bird. You can't really make it about laying eggs. You can't really make it about flying. You can't really make it about having wings. Like, I'm not a biologist, but there's the things that humans commonly would consider birds, if you ask them on the street, don't actually have a very specific set of defining common characteristics. So she asked them to tell her how much they considered something a bird. And that's a really revolutionary thing about it. And then came up with something that is rather funnily called a birdiness ranking. How much of something a bird? And when you find out that a robin is very much a bird, and a penguin is sort of on the outskirts, and so is an ostrich, but in different ways, right? They're both kind of birds, but not really, is how people feel about them being birds, but in very different ways. So the idea in prototype theory is now that this is fundamentally how word meaning works for humans, that categories do not have clear boundaries, but we can sort of agree on how much something belongs to a bird, but that the representation in the brain is inherently fuzzy. And that we were able to represent sort of how much something belongs to a category without, as humans, for our processing, really needing the idea of clearly defined categories. So this was sort of very linguistic. So now let's move back to NLP and what was happening with meaning in NLP. So the first interesting thing to happen here. I'm sorry,
Can I just interrupt for 1 second? I think the GP123 wants to ask a question. There is a hand that is been raised. Yes. So if you want, you can unmute yourself and you can ask your question if you have one. And if not, we can go on. So... Okay, so if you want to ask your question later, you can ask it later. If not, we can go on. Thank you.
All right. Let me just try to switch back to the slides. Yes, okay. So going from this sort of bunch of very linguistic, philosophical stuff about what really is the meaning of a word, let's look at how this is actually relevant for NLP. So in the 1990s, you get the first representation of something that's kind of similar to what we do today, which were count-based word embeddings, which were these things where we just counted how often words occur together. It was very, very sparse, and it looked kind of like this. You'd have a sentence like the dog barked in the park, the owner of the dog put him on the leash since he barked, and then you'd come up with a table like this where you would measure co-occurrences and you see that you get lots of zeros. But if you think about what sort of linguistic theory this corresponds to, you can realize that this is like the first implementation of distributional semantics, right? This is the first implementation of it's relevant what company the words keep. So at the time, it wasn't really very practical just because you need a lot of data and you'd end up with a lot of zeros and they couldn't really figure out something to do with it. So something else that became popular around the same time was WordNet, which is like squarely in the formal side of the debate again. I'm sure that you've all seen WordNet at some point. So it looks kind of like this. Car is something that we'd anchor here in a whole hierarchy of things, and it sort of gets more general as we go up, and you sort of try to classify. It's really amazing how many things are in WordNet. They've basically thought of everything, and they've sort of made an attempt of classifying everything as a type of some other thing. And you can see now that it's manually compiled, right? It's got all of these relations like synonymy, hyponymy, meronymy. Like meronymy would be like siblings here, and hyponymy would be hierarchical relationships. But you can also think about this would really struggle with more abstract concepts like this sort of entity and conveyance and unit sort of feel very made up. But mostly what I'm trying to say here is that this is again very formal, very clear. You're clear on what belongs where, on what the criteria are. They actually sat down and thought about them, and you don't get this sort of fuzziness and context thingy. And WordNet is something that we still use today. But then mostly what we use right now to represent meaning is trainable word embeddings, right? So in 2013, there's a breakthrough on how to use trainable word embeddings because Mikolov et al. Come up with a way of getting lower dimensional ones with continuous bag of words and skipgram. So this now leads to word embeddings just like we had before, but suddenly they're not so horribly sparse anymore, and we can train them much more efficiently. And now we get to see these sort of emergent compositionality things, which are very, very exciting. At least they were very exciting at the time. So at the top here, you can see that you get all of these nice effects that you sort of want anyway, right? Like you want cat to be close to kitten, and you want dog sort of to be further away, and then you want houses to be really further away. So this is like a first proof of concept that actually distributional semantics as a paradigm for computational linguistics can really work. But what's even cooler is you get effects like compositionality, where you can subtract a vector from here and then you can add it here, and then with the same thing where you get from man to woman, you can get from king to queen. But on the other hand, at the same time as this, the sort of formal idea of meaning is still there in something called AMR, abstract meaning representation, which is also still being used today. So in AMR, if you have a sentence like this, like the boy wants to go, then you can represent it in these sort of formal graph-based or logic-based ways, which I'm sure you can now connect to what I was saying earlier about the logical forms with the Socrates sentences. So this is basically the computational and standardized version of that. Like they really worked out how to make this logic form work, and they wrote a whole syntax for it, and you can have it graph-based, and there are whole like tasks, and there's AMR parsing, and it's still being used for lots of things. So it's sort of this counterpoint to the more fuzzy distributional semantics-based word embeddings. All right. So this was basically like the historical half of my talk, but now let's get to the really current issues, which is when these debates are transformers now. Because I haven't come to that yet, right? I stopped at RNNs with attention, and then I stopped at static word embeddings. So let's now together move on to transformers with both of these topics. So are transformers the victory of connectionism is the obvious question, because if you look at something like this, and when you think back to the Rumelhart-McClelland, then it sort of seems like now we have the perfect connectionist model, right? We have language understanding without any structure. We haven't given it any sort of supervised input. We haven't given it an innate bias for rules, nothing of the sort. And it's learned all of this stuff from unstructured data, just like Rumelhart and McClelland originally wanted. And what we also have on the meaning side of things is now we have context for a meaning. So this is sort of like distributional semantics on steroids, I guess you'd say. So we've acquired a bunch of meaning without any formal structure, because now we have contextual embeddings. And we can see that they really work, right? Like I'm sure you've all seen graphics like this, where if you compare BERT embeddings with earlier static embeddings, and then you sort of annotate the meanings in context, where these are all occurrences of bank, and when the pink ones mean bank as in a financial institution, and green ones are like a sloping land, so like the bank of a river, then you can see that they actually do sort themselves by context without us having done anything at all. So it's like a further progress on distributional semantics really seems to work in practice. But there's also counterpoints to how well we're now representing meaning from an entirely different perspective, from people who are questioning if we can have meaning purely from text. So this is a thought experiment here from the Climbing Towards Natural Language Understanding paper from the theme track of ACL 2020. They had this thought experiment of you get two people on separate islands, and they're communicating via an underwater cable, and there's an octopus listening into them. That's why this paper is also famously called the octopus paper. There's an octopus listening into them who's living in the sea, and therefore he's got no concept of what they're talking about their lived experiences on land, because he's only ever seen the sea. So he can only see the data. So the octopus is supposed to be a language model, is the obvious analogy here. And if one of them is now telling the other that he's being chased by a bear, then the octopus can see that. But if a bear's never been mentioned before and the octopus can't have seen a bear because there are no bears underwater, usually, I guess, then he has no way of understanding what this person A means when they say they're being chased by a bear. So then when you ask, so at the time it was GPT-2, so then they asked GPT-2, help, I'm being chased by a bear, and GPT, all I have is a stick, what do I do? And GPT-2 said, the bear is chasing me. So it's basically just repeating some stuff. So the argument that we're trying to make here is that the idea that we can acquire meaning purely from text is sort of futile, because language models can't look at the real world that we're talking about, and therefore they're also always going to miss connections and miss stuff that's going on in the real world, because it's impossible to learn all of this purely from text. But okay, even if we accept that we can't have true language understanding, mostly because language models aren't conscious, then I think it's still interesting to, I know a lot of other people think as well, but it's still interesting to look at how do the models now get where they're getting. Have we really learned structure from text? So something that's also been going on in the last few years with transformers is that people now do probing from a linguistics perspective. So I'm not sure how familiar you all are with this, so I'll just introduce it again. So the the idea is that people wanted to test how well BERT really understands syntax. And to do that, they sort of went back to formal syntactic structure because they needed something to test against. So there's this famous paper by John Hewitt and Chris Manning from 2019, where they looked at universal dependencies, which is basically a form of formal grammar, as the correct way of looking at sentences. And now they ask, does BERT correspond to this? There's a whole probing methodology here. So basically, you can look at the attention heads in BERT, and you can see how well they correspond to certain relations in universal dependencies. And then, for example, you can find a head where the noun premodifiers, so like adjectives and determiners, attend to their noun 95% of the time. So the reason why I'm mentioning this in a talk about how linguistics shaped NLP is that now it's shaping NLP again. The formal syntax is shaping NLP again because it's being used to look at how language models learn and to sort of assess its capabilities. But it's a conscious choice, right? It's a conscious choice of which theory do we use to make statements about if language models are doing something right or wrong. We can even do trees, like it went pretty far how they were able to match universal dependencies to BERT. So with a bit of training of like a simple, some simple matrices, they even managed to extract whole syntactic trees. So this is supposed to be like a very flat representation of the sort of syntactic tree that I showed you earlier. And basically in black, you get a human annotated tree of this sentence. And then in blue is something that they learn from BERT. So it's basically identical. And they're arguing that therefore BERT has learned to internally represent things in this tree structure. So now we're arguing that this sort of connectedness model has really internally acquired some sort of formal tree structure. So does this now mean that we've constructed a model that can do both, that can do all of the connectionism, but it's also acquiring the structure? But not really, because there are some recent studies that have shown that they actually don't really conform to formal syntax, to the things that formal syntacticians would want. So here's an interesting example. They came up, so this is natural language inference. So basically you always have one premise sentence, and then the model is supposed to say if this following sentence, the second one, is right or wrong based on the first sentence. And so basically Tom McCoy and some co-authors of his designed some traps for the model to fall into. So you get the lexical overlap trap, where the doctor was paid by the actor, and there's like a huge lexical overlap with the doctor paid the actor. Basically, they've just removed two words. And they wanted to see, do models automatically assume that this is right? And another one is subsequence. So the actor danced is a substring here in the premise. And now they wanted to see, do the models just assume that this is correct based on the fact that it's a subsequence? And here it's the same thing. So if you get this sort of subsequence, the artist slept, the actor ran, in this example it's actually wrong, right? Because it's just an if. So basically they wanted to trip up the models to see if they actually have structural understanding of what's going on in the sentence, or if they're just picking at the words. And what they found was pretty depressing. So you see in the bottom here is the accuracy for the sentences where there was no entailment. So like these, where the correct answer was always wrong. And then here you see the accuracies for words entailed. And you can basically see that the models were predicting entailed the whole time. And you can see by making like a tiny improvement, like it's definitely noticeably better than older models. but not really to any degree where you'd consider it to have any sort of formal reasoning about this. And it's not even chance, right? It's not even a chance. It's much below chance accuracy. Or here's another example of where people are criticizing how language models are reasoning about language at the moment, which is about compositionality. So linguists want language models to be compositional. So here's an example of you can do a hedgehog ate the cake. So hedgehog is the subject. And then generalization would now be to realize that you can also use a hedgehog as an object, as you can also do the baby liked the hedgehog. And you can see that the accuracy of transformers in this is actually really bad. Like it's having a lot of trouble generalizing from seeing something as a subject and then using it as an object. The other way around seems to be working marginally better. So you get these dots here. And then you just get stuff that is pretty basic to a human. Like I give you the name Paula. Like, okay, let's say that I just made up a new name and you've never heard of Paula before. I say, okay, Paula, and then you're supposed to use it in the child had Paula, and language models just can't deal with this at all. Or from active to passive, that's actually really interesting because the transformer is doing really well on that. So what I'm trying to show here is that you now get the exact sort of formal theories that we were talking about earlier from linguistics, but are being explicitly used to assess language models, because it's not arbitrary, right? Like for this, for example, you need to agree that subjects and objects and proper nouns and PP modifiers, which are like a syntactic technical term, are actually how language works. And now you use this as sort of like a gold standard to talk about how well the transformer is working. So one last question would be, so we do need that sort of compositionality. People seem to think that we need syntactic structure. Now, there's also work on, can we now inject structure? So you get models like this, where somebody's taken, some friends of mine took a transformer, and they explicitly gave it some syntactic structure to learn, along with language modeling, to sort of manually inject the structure. But it actually turns out that this is only beneficial when you don't have a lot of data. And when you have a lot of data, it turns out that you don't really need this, which again sort of makes you assume that language models are really internally representing this. And so this is just some final food for thought. Some questions that I'm discussing now in my mind and that I'd like to discuss with you is, so from the perspective of linguistics, does the success of neural networks now count in favor of connectionist modeling? Because we have neural networks and they seem to be doing pretty well with language. Is that something that's now going to convince some linguists that connectionist modeling works and that you don't need explicit sets of rules? But also we're improving on ever larger data sets. So is that really going to mean anything to the linguists if we're using so much data, so much more than children are probably exposed to? Here's something that you will probably find more relevant, which is for NLP, how do we want our models to develop? So right now, I'd say that formal syntax and formal semantics has mostly taken a backseat in NLP, except for the sort of probing literature that I showed earlier, right? Because if we're still using formal syntax or formal semantics to describe how well transformer models work, then we are still using them and they're still having an influence on our thinking. And I just think that's an important question to consider. And then I guess for the more machine learning oriented people, there's a question of if these large neural networks are developing biases towards structure, how are they developing those? Like I don't know enough about the mathematics of that to really make an interesting statement about that, but I do find it an interesting question of if we had different architectures, would they develop different linguistic biases? Like people, for example, often say that a disadvantage of leaving RNNs is that you now no longer explicitly have this sequential structure of language encoded. So that's something to think about. Yeah, so this was basically my talk. My discussion question is now, very briefly, how should language models learn language? Yeah, thank you very much for listening. I'm just trying to get
Thank you. This was very interesting and very all-encompassing. So I would like to start off the question round with a tweet that we read a few days ago. It's kind of very relevant to what you're speaking about and also to all of the questions. So the tweet says, "It's easy to understand why linguists hate large language models. Imagine dedicating your life to enumerating consistent models for the space of human language. Then a bunch of nerds come out of nowhere with a simple gradient descent black box, simple, that accomplishes miracles while disregarding your field," which is, of course, it's not a scientific statement, it's a tweet, but it's kind of funny because so the
could you
name,
send a link in the chat or something? I find this really interesting.
I will, yes. So I'm gonna send the link, and I find it kind of interesting because on one hand, linguistics is kind of missing from NLP research a lot of the time, and it's being basically pushed away by just scaling up models into infinity. Not always, but sometimes we just use emergent structure. So we're just hoping that the computational power is just going to make up for not using, because large language models don't learn the way people learn, of course. It's just, yeah, just like neural networks are not actually working the way neurons in the brain work. But we kind of go full circle because with like probing, you can see sometimes how language models learn, and it's really interesting if you probe models to see what kind of structures they just pick up on. And this is also a little bit like language in humans, because language hasn't been standardized for that many years. So up until like 100 or 200 years ago, language was pretty non-standardized, especially around dialects, and there wasn't really one single language that was that is managed by a single institution like today in most countries. So it's interesting because the way language models learn, they have like their own path of learning, just the way humans acquire language. So it's kind of interesting to compare both of them. And I see that I'm gonna post a tweet right away in the chat, and I see that we have 2 questions in chat. So yeah.
Can I just quickly say something to that? So
yeah,
what those are some really interesting points. I guess one of the reasons why I like talking about this in terms of the joint history and in terms of all of this connectionism and fuzzy representations, distributional semantics, is that something that bothers me personally in the perception of linguistics from NLP is that it sometimes feels like only one theory is visible. Like if you look from NLP and you don't have a linguistics background and you think about syntax, you think universal dependencies and that's it. That's basically what you think. Or for semantics, maybe you think like abstract meaning representation. So there's so much diversity in linguistics, where some people are in their theories a lot closer to how language models are doing stuff right now, and some people are far away from that. But I suppose the some of the historical development has just caused it to be such that the linguists that are sort of advising NLP right now are mostly in the camp of formal stuff and of dependency syntax and of rule learning. which is sort of ironic given that that is not what turned out to work. So that's also something that I'm personally really passionate about in my research, to just try to get more theories back into NLP that are more cognitively plausible, because I think they have the neat side effect of making more sense for language models as well. If people want, you can check out my Twitter, because we just put out a position paper on what we think should be done with probing at the moment, just like a month ago. That's maybe something that might interest people. But yeah, sorry, I'm taking time away rambling from people to ask really interesting questions. So please go ahead.
So this is the tweet. I pasted it in the chat. If you're watching from YouTube, we're going to paste it in the description also. So I just want to add on to what you said, and then I'm going to ask Muniz Ali's question, and then we're going to go to GP123, so he can ask his question. It's very interesting, and it's also, this is why it's great that your kind of research interest is not only in structure, but also in cognitive linguistics and how it ties up with NLP, because not only does, even on a structural level, language models don't really learn language the way language actually works and just the way language is learned. For example, if you take a BERT tokenizer, on coincidence, it might actually segment words into how they're linguistically and logically segmented. If you have like a lemma and then some kind of a suffix or a prefix, but a lot of the times it's just a statistical tool that sees, okay, this is a pseudo suffix that comes 1,000 times, so I'm just going to segment it every time. And obviously this doesn't make a linguistic sense, but at the end of the day, you take a BERT sentiment analyzer, for example, and it works. So we take it and you say, okay, it works. But then when you add on to the cognitive linguistical perspective, it gets even more complicated, because you have this this triad of stuff that we don't really understand, but it still gets trained and it works. So it's, I don't know, I found it really, really fascinating. So yeah,
that's a good point. Like, there are essentially, looking at the way that the tokenizers work, there are two ways in which you could react as a linguist. One of them would be to grumble about the fact that it doesn't really correspond to how the morphological segmentation is supposed to be. And there is indeed work by a colleague of mine from CIS, Valentin Hofmann, who looked at how you can improve BERT if you actually run morphological segmentation first instead of tokenization. But what I would always argue for is, it turns out that morphological segmentation in the brain, the way that morphemes develop and the way that language structure develops, is also just based on frequency and statistics. It's just that we have access to so much more data. Like, there's so many more factors involved. Like, I don't know how distinctive morphemes sound and how we pronounce them. And it's basically, I would think that at the core, it's going to be something that's similar to word piece, where if you just, the most frequent things just build units together. But it's just that there are so many more factors involved than if we have a simple text-based language model, that we do end up with different segmentation. But I think that's an argument for developing more complex models of that, so we can actually computationally re-engineer how this sort of segmentation works, instead of prescribing how we think morphological segmentation should work, and then telling the model to do that, and then being really frustrated when it doesn't work as well as simple heuristic tokenizations. Oh, somebody asked about beginner-friendly literature about linguistic theories. And depressingly enough, I don't actually have a recommendation.
Just a general, it's not necessarily concentrated on theories, but I want to ask the questions in order, but I'm just going to paste the book from Emily Bender. She's great.
Oh, no. No.
It's just like an overview. So this is just a general linguistic overview. It doesn't focus on theories, but this is just a recommendation for overview. But we can
I'm sure
post some.
found it great. It's just something that I found is that it's very difficult to find a linguistic textbook that covers all of the perspectives, just because linguists all have opinions, and so you sort of get introductory textbooks that cover one perspective and ones that cover different perspective, and you get entire classes in linguistics taught from one theory without ever mentioning any of the others, just because it's a personal favorite theory of the lecturer. So I am yet to find a resource that is somehow objective over this. And I think that also covers Emily Bender's book. But yeah.
So the first question was a semi-question, semi-compliment. So Muniz Ali says, great talk. I like the argumentative flavor of the talk, especially the distributional vs compositional slides. And yeah, so GP123, you can actually unmute yourself now if you want. He said he wants to ask the question.
Yes, can you guys hear me this time?
Yes.
Yes.
Okay, sorry about the technical glitch. Yeah, I had a question. This is actually a really relevant talk to a lot of things I was thinking about recently as well. But I wondered if kind of similar to, evolution, humans have developed like the neural circuitry to be able to process language, which more recently, like people have argued is distinct from, reasoning ability as well. So I had two questions. One was, I wonder if people have utilized or are thinking of utilizing deep learning as sort of the way to ingest language, but then apply, like similar curriculum learning to how humans learn grammar through, say, school and education, to develop like these principled rules and maybe develop a systematic way of thinking about language. So kind of combining using the large language model pre-training as sort of the evolutionary circuitry that we have developed over the years, but then also utilizing some kind of curriculum learning to mimic how humans have learned in a more principled manner. That's my first question. I also had a second one, but yeah, if we don't have time, I understand.
Maybe I can just quickly answer the first one, because I'm sure my memory is great enough to keep two questions
no problem.
At the same time. So interesting idea, but I'd actually just not agree that makes a lot of sense, just because I don't think it's necessary that we learn grammar in schools. I mean, sure, it probably is for some minor post-editing of what people have learned, and probably also for like standardized spelling. But I've always, I can't exactly cite any studies on this, but I've always found that at least in your native language, the fact that eventually if you go to school, somebody teaches you what a noun is, doesn't really change the fact that you were speaking your native language correctly the whole time. So because we learn what a noun is, we're now able to consciously reason about the structure of sentences, right? Which may or may not be helpful for some sort of tasks, or for describing some ambiguities in sentences, maybe to other humans. But I wouldn't think that it's so central to our language modeling that it's necessarily a skill that we need language models to what is the word I'm searching for? To do similarly as we do.
Well, I guess the reason I ask is back to your point, like whether the LLMs are learning to copy and paste really well if they have enough data versus learning like formal syntax. So I guess I wondered if like the grammatical teachings kind of show how to form rule-based syntax.
Yeah, interesting
or if it's
question.
through another way. Yeah.
I'm so sorry, what was the other one? The other question?
Oh, the other question was kind of related to the octopus example. I was also thinking about that. So I think the octopus example in my mind was how do we sort of project our understanding of entities in the world? And I think to your point, like that may be impossible to do with a single modality. So for something like that, we may have to integrate like multimodal information with images, but there's still kind of an area that images would not cover, which is like abstraction. How do you express articles implicitly? Like, I don't think an octopus could understand what the means with anything in the world necessarily. Maybe like a video modality would help. But my point, I guess my question was, is there kind of a formal framework for decomposing the different aspects of language that we need to cover? So I suppose like entities would be one. I don't know if abstraction would be another one. Just kind of to track the progress that we're making in fully modeling language and I guess the world through language.
Oh yeah, that's a tough one. So first of all, I'm not entirely sure that a language model needs to understand what the means. But again, that's just my personal opinion on the spectrum of meaning. So I would say that as long as you can use the in context, it's not really important that you need to reason about what it means. But then the second part of your question I found really interesting, which was, is there a formal framework of what are all the bits that we need to teach language models to get there? Which I find really challenging. So for that, there would basically have to be a consensus in linguistics for how we do it to even be able to cover the full range of things. Like, sure, what we're doing at the moment, I guess, is with probing or just with general evaluation benchmarks, we are just, as a community of researchers, pointing out things that language models are not doing correctly. But just because we're pointing them out separately doesn't mean that they're necessarily separate things, right? That the language model would need to address separately, or that humans are addressing separately. I think there are plenty of examples historically where people have been like, oh, language model can't do this one specific thing. We should build something on top of it so that it can do this one specific thing. And then 2 years later, it just solved itself because the language model got bigger. And that for me also raises questions as to, do humans really do this specific thing in a specific way? But I would certainly agree about multimodality. I mean, I think there's no way to argue that we won't eventually need multimodality for language models to develop some advanced reasoning, like for, you know, physics reasoning and stuff. You can always find text-based tasks for which you would need multimodal reasoning, certainly. It's just not something that's concerned me in my research personally, but there are lots of great people out there doing that and arguing for it, and I think they are certainly right.
This actually ties so well into the next question, that is, can we run into the risk of making large language models less adaptable for multilingual NLP by explicitly injecting language structure?
That's an interesting one.
Very.
Okay, so I'm not in favor of explicitly injecting language structure in general, just because I don't agree with the language structure. But let's think for a second that I was. So there's something that we're working on at the moment, which is to see how what I didn't get into at all in this talk is that language structures are vastly different, right? If you look at the structure of something like Turkish or Finnish, and then compare it to the structure of a German and the structure of, I don't know, Hebrew, then you would find such different internal workings. Of course, a Chomskyist would argue that they're really fundamentally all the same, and you just need to account for a bunch of parameters that make them different. If we're talking about injecting something like UD into language models where we don't have a lot of data, which is something that we suspect, we're currently working on proving it, but what we suspect currently still helps performance, just because for lots of languages there's not a lot of data, so there's not enough data for them to acquire structure implicitly. Then I would actually think that it makes for more adaptable to multilingual NLP, just because something like UD is explicitly designed to have so many compromises that it basically has the same categories across all languages, right? So if that's the sort of language structure injection that you're thinking about, then I wouldn't be worried. However, if we go beyond that and think about the fact that UD is a massive overgeneralization and also a gigantic compromise between languages that are really at the bottom of it very different, then maybe you could get to a point where you could argue that you're really harming something by explicitly making it follow UD, because maybe UD only makes 95% sense for this particular language. So yeah, so I'd say there are pros and cons, but really interesting question there.
So Muniz, if you want, you can unmute yourself and ask the question yourself. And if not, I can ask it for you, however you want. You can unmute yourself if you want.
Hello, hello, am I audible?
Yes, you are. Hi.
Yeah, hello. So I'm a researcher here. I'm a master's student here in Saarland University, and you quoted like one of the professors, Alexander Koller's, like the Bear paper. I actually was just curious about, because I took like these classes from the linguistic side as well, but my degree is like on the sort of applied and technology, like data science side. I was just thinking, like, in terms of like this conversation that you sort of described between like the schools of thought, if you will. I was just thinking, like, in terms of like this, in terms of like when we would have like, let's take the example of like translating languages. So this sort of thought and also question ties in with like the colleague who was asking before about this multilinguistical, this sort of multilingual NLP. But my approach is sort of like, from the lecture I took was about machine translation. It was taught like by a linguist, like a computational linguist. And we were sort of taught that we first have like this sort of triangle from the source language, the hierarchy like moves to a syntactic structure, then semantic, and then the interlingual representation, so the Wacky triangle. So I was just, and then throughout the historical perspectives, exactly like you were sort of presenting, like how the evolution happens, or if you would even call it evolution. So in this sort of a triangle, as the machine translation systems from like rule-based to statistical, like in the end, what we see now is in the end, it's like the neural machine translation, the NMTs, it's like a heyday. So I was just thinking in terms of having this triangle in front of us from the linguistic sort of side, and seeing that in the end, we do want like to have some sort of a thought level representation of language, which is achieved in like from the computational side via, say, embeddings. And so I see like this sort of a coming together of the two sort of academic traditions, if you would want to call it that. But having said this, how do you look at the field sort of evolving from there? Because now when we look at this multilingual, so there's like in the multilingual NLP space, we also have like the huge problem of like low resource languages and other things. So I just want like to know your take, like, you know, how to sort of inform the computational training or developing these models from the linguistic side. But we do have like from the linguistic side, this interlingual thing, it can be achieved already like via embeddings, multiple tons of them now. So how do you look at this thought? Like, so first like the general take, and the second is like, how would you then sort of advise us to sort of approach low resource languages as a linguist? What do you have the training data for? Thank you.
Okay, thanks for the question. Let me just, I hope I understood it correctly. So about interlingua is an interesting discussion. And I find it interesting that you would say that embeddings would be an interlingua. And I do get your point, like they are a sort of interlingua, right? In that we can now get something like mbert to develop some sort of meaning representation that is language universal, but it's not interpretable, at least not without a lot of effort, which I kind of like. So what always bothered me about the interlingua idea in the machine translation classes that I took was that it was advertised as sort of like abstract meaning representation, right? As this interpretable thing that is
Very
how more efficient than individual languages. I mean, now they're coming up with universal meaning representation is something that they're trying to develop right now, which basically works into this original idea of an interlingua, which I really fundamentally dislike. And the reason for that is that I believe that language is already a perfectly efficient system. And if it were possible to design a representation which covers all the aspects of the meaning of a sentence and is somehow more concise, then I think language evolution would have already taken care of that by now. And what I've seen so far from all of these formal approaches is that you always lose something about the meaning, which is natural because you need, like, if you weren't losing something about the meaning by making it shorter, then like efficiency processes in language evolution would have already taken care of that. But I suppose I could be on board with an interlingua if you would consider multilingual sentence embedding an interlingua, even if it's not interpretable. So then about low resource languages, I'm not sure I 100% understood what the question there was, but
my question for that was, like, if I could put it more concisely now, it is about, like, for the other languages there is already data available. So like for most of these models are like basically it's predictions based on context and like next word stuff. For languages which do not have that tendency, or sorry, that data, I was if you would have some suggestion, because in the machine translation class that I took, we sort of looked at like SVO languages and like object verb and all these others, these sort of language families, and there was always like this problem of alignment which one had to take care of, and that is like when the statistics and then like proceeding on to neural machine translation stuff, these problems were somehow alleviated. But I still like, I'm looking at like a language which is very low resource. So do you have like some semblance perhaps of to sort of take like a computational a linguistics tool or technique to help?
So I personally really like it that the alignment problems have gone away. Like, I know exactly what you're talking about because I still have research where I would actually need word level alignment to really low resource languages for linguistics purposes, and we basically can't get that. But for machine translation, we don't need it anymore, which I do kind of like, because I think that with something like that, you're always going to lose language diversity, like because you're trying so hard to align it to something like English, when really the concepts don't really correspond. But for how to ultimately deal with this sort of diversity, I don't think there's an easy answer. What I'm always interested in is if we had enough data for even low resource languages, then we could make so many much more interesting data-driven statements about the full range of diversity that exists in the languages of the world. Like, that's something that I think about a lot. But a lot of the theories which are sort of limited and work only for high resource languages, or the methods, have simply been developed because people didn't bother to look at other languages, and so they didn't see the full range of weirdness, I suppose, of strangeness that is out there. And I find it so interesting that we now have computational methods of looking at that, but what to do while we don't have enough resources for that, I'm afraid that there's also not a simple answer there from linguistics, just because you have to respect how different languages really are, what sort of enormous breadth of, I mean, not even just word order, like so much variety there is out there. And it just makes it really challenging, yeah.
Before going to the next question, I'm just going to do a slight self-promo relating to this question. So this is our talk with Sebastian Ruda, and we actually talked about underrepresented languages. So you can, if you want, you can look at this. Also, I mean, there is obviously no straight answer, but this is an interesting talk, and he talks about the challenges. And the next question is from Daniel. He asks, is there any research on whether word embeddings match up with prototypes or semantic spaces, And in parentheses, is vector for robin closer to bird than penguin, for example?
That's a really good question. I feel like there is something. So I don't think people have re-examined the original studies again, just because the original studies are so small. That's honestly the answer. I mean, just if you look at Eleanor Rush's first studies, like how much time it takes basically psychologists to collect this data about humans, the experiment would probably just be you look at the vectors for all of these birds once, and then you see that they have the approximate level of closeness that she said, and then you haven't done enough to make a paper out of it. But I feel like so what I immediately associated with this is a paper by some friends of mine about contextual embeddings in BERT, where they looked at it as multi-prototype embeddings, because of course prototype theory sort of only works if the word only has one meaning, right? If there's a universal concept of BERT, and then it can all sort of cluster around it. But there are lots of ambiguous words like bank, where you could think about it as sort of multiple prototypes for this one word. So what's also interesting here to mention is that from my sort of perspective, prototype, and from lots of, I mean, this is not something that I come up with, but there are lots of cognitive linguists that consider prototype theory to be hugely important, but not just for stuff like birdiness rankings. You can actually look at prototypicality effects in pretty much every level of representation in language that there is. You can get prototypicality effects for phonemes, where there's like one way of what an O should sound like, and then there's a cluster of things that are sort of similar around there. You can get prototypicality effects for syntax, for something that is stereotypically a noun, and then things that are kind of a noun, but maybe not really. Like this sort of principle of a fuzzy representation with some things belonging more and some things belonging less, and there being a frequency distribution of lots of things in the center and then less things around it, is just something that happens again and again and again in so many areas of the human brain and also in language, that I'm sure you can observe these sort of effects in lots of places, but I'm not sure if somebody's actually followed up specific on the bird thing, but I would think off the top of my head that it's trivial and that it just turns out that it corresponds really well to the birdiness rankings, and that's it.
So Muni's questions were answered, I think. So the next question would be from Rodrigo, maybe related to the multimodality topic. Are there any studies about how blind and or deaf people learn a language and what difficulties they face in the process?
Okay. I'm actually not that familiar with like the linguistics of sign language, but I will do a shameless plug for a friend of mine and his invite to talk about the topic. Give me 1 second, I'm gonna have the link for you. So if sign language processing is really like its own topic, and in this you can also find out something about the linguistics of sign languages, which is like a whole thing. Like sign languages behave like normal languages in really, really interesting ways, but they're still way more difficult to process just because of the multimodal stuff and the hands moving and the. So this is a talk that you could check out about sign language processing if you're interested. And then what also comes to mind there, I mean, this is not exactly about blind or deaf people, but sort of about universal processes of learning languages, is that there was a really interesting keynote at EMNLP last year by, oh God, give me 1 second, I'm gonna remember. Actually, I'm going to use the internet to remember, which I think is what people do these days. by Neil Cohn about the multimodal language facility in the visual languages of comics. I'm just going to copy the link here to the keynote's abstract overview. I'm not sure if they recorded it somewhere. Maybe they did. Where he argued that visual language in comics actually has a lot of similar properties to normal languages, and that you sort of get micro expressions, and it's sort of compositional to larger panels. And that's also something really interesting to think about. Blind people, unfortunately, have absolutely no interesting input on this. But yeah, this should definitely be considered in theories in linguistics, and that there should be something that's universally happening in the brain that is joined with sign language, and then there should, I guess, be things that diverge between sign language processing and regular language processing. But I'm afraid I don't have any good studies to share. Huh. Okay, sorry, what's the...
Alternatively, have there been any studies on people or represent concepts or entities without being able?
I'm sorry, maybe I'm having an internet problem, or Martin, you're having an internet problem, one of us.
Can you hear me now?
Yeah, I think so.
So the question was, alternatively, have there been any studies about how blind people are able to represent concepts or entities without being able to use imagery? And before you answer this, I'm going to do a plug for a friend of mine. She is a really she's a really so she's a PhD student, and she actually specializes in sign language and linguistics, and you can reach out to her or check out her publications, and this is just like a tip. So yeah,
well, for me this doesn't work. Maybe that's just because I'm not on LinkedIn. Yeah, so Annika Schiefner is her name. You can find her on LinkedIn. This is just a heads up for the people who are interested in sign language. She does many different stuff. Yeah, thanks. So about I'm actually not familiar with any studies. That's a really interesting question. But something that I would think about it is that it's not just the fact that we can look at stuff, right? So there are multiple different things. So if you think about the example that I was once given that really stuck in my head, was if you're trying to explain to a child what a cookie is, right? That's probably why it stuck in my head, because cookies are nice. So you could presumably learn properties of a cookie from seeing cookies in lots of sentences, and sort of slowly inferring, like we saw earlier with the Wompy mark, if that were a cookie. But if you have multimodality, then you can point at a cookie, and the child will have already collected lots of properties of cookie just from seeing the cookie, like before it even learns to speak, right? And you can just be like, that's a cookie. And then all you have to do is link that to the already formed representation. But I would think that even for blind people, there's going to be a pre-computed representation of a cookie in terms of how the cookie feels and how the cookie tastes and how the cookie sounds. And I think that's going to make it much easier, so then language doesn't have to do all the heavy lifting. That's actually, that's, I guess, a way that we can think about what language models are doing right now, because we don't have A, conscious reasoning, and B, multimodality. And I mean, any sort of multimodality, not just visual, I mean, also touch and feel, those are the same, touch and taste. Then language modeling just has to do all of the heavy lifting. And it also has to do the heavy lifting for lack of consciousness, right? So if I see a sentence about a cookie and I don't know what a cookie is, then I can just ask the person saying the sentence what a cookie is, and then they could give me a definition of a cookie, and then I can consciously reason about this definition of a cookie, and I can use that to update my state of mind. But language models are actually still really struggling with processing definitions and matching them to context. So I can plug another paper of a colleague of mine where they have a, so this is a paper about a natural language, about a benchmark that most big models still really struggle with, where you have addition of a mask token and you have a context for mask token, and you have 5 of each and you need to match them together, just from inferring from the definition and the one context that you're given. And I like plugging this one because I was the human baseline for this one. Me and Timo Schick were the human baseline, and we are still unbeaten by the models. And this got integrated into the Big Bench paper, and they did another human baseline and they performed worse than us. So that's why I like plugging this paper. But that's a whole other resource that humans have that language models don't: conscious reasoning and being able to process definitions.
So usually we ask a question at the end, but I think it's a really good point that you're making. I want to reiterate that language models do not have conscious reasoning, which, if you're in the field, it's very obvious and it's kind of self-explanatory, but especially in pop culture and media and so on, I think it's very much important and really needed to reiterate that language models do not have conscious reasoning. And they're actually, I think there was also some kind of a meme that they're just really good maximum likelihood estimators or something like that, which is very true. So this is a really good point that I think needs to get out there more, so people understand how these things work, even if they're not a NLP professional. So at the end, we usually just ask people if they have, do you have some, if you read an interesting paper lately, something that personally interests you, a specific scientific interest, just something that you can share with us, very, unofficial.
So the papers that I read are very specific. So the stuff that I'm currently getting excited about would probably make more sense if you'd seen a talk about my actual research area, which is like this whole other bucket of stuff.
Which is fine.
Something that I recently really liked, a really creative paper by Kyle Mahowald of UT Austin, is he looked at, he figured out a way to reason with ChatGPT essentially about how it views language. And I'm just going to zoom in on the part of it that I think is really, really universally understandable, which is the following idea. If you have ChatGPT and you find a prompt that performs very well on the COLA dataset, so that's linguistic acceptability ratings, where you just ask the model, so you can just ask the model to rate how acceptable do you find this sentence. And there's a whole benchmark on this, and so you can manually find a prompt that works well for this data set. Then you can basically start asking it any sort of test sentence that you would like, and ask it if it finds this test sentence acceptable. And then you can do something that linguists really might like to do, which is something called minimal pairs, where you take a correct sentence and you change one tiny thing about it, and then it's wrong, but you know why it's wrong, because it's this tiny thing and you've changed nothing else. And now that you get to prompt ChatGPT for, do you find this sentence acceptable? Do you find that one acceptable? Do you find this third one acceptable? You can use that methodology to, in a very fine-grained way, find out, how it, well, reasons is too big of a word, but to find out more about which sentences it thinks are valid and which not. And that's something I recently got very excited about. And really want to try out on some more different types of sentences. But I realize this is extremely niche to my field of research.
So all of these papers that we talked about, are are in chat, and if you look at the YouTube video in a few days, they're also going to be there in the description, so you can look them up, do your own research. And yeah, so this was extremely interesting. I really enjoyed that. I think with all these questions, people really enjoy that too. Thank you for taking your time. Everybody check our events. We have 8 events in the next month. So yeah, thank you everybody for coming. Thank you, Leonie. This was really,
thank you
really
very much. Thank you very much for having me. Thank you for the really interesting questions and really cool discussion. It was great.
Thank you. And you have a great evening. Thank you.
You too. Bye, everybody.